मेरी colleague हैं उसके जी
Dr. should we go ahead? Okay. Sorry, just a second. Right. Kia ora tēnā koutou katoa. Assalamu alaikum and welcome everyone to the New Zealand Pakistan Research Forum webinar series. Today is the 24th of September 2020 and I'll be your host for today's session. So I'll start with my quick intro. My name is Dr. Fahim Abbasi. I'm a cybersecurity researcher, defender, and innovator. I have over 10 years of cybersecurity research and industry experience while working for leading cybersecurity companies in the US. I'm currently working as a senior cybersecurity researcher at Trustwave here in Auckland. Next, an introduction about the New Zealand Pakistan Research Forum. So the New Zealand Pakistan Research Forum was established in 2019 by my mentor and very good friend, Dr. Mohammed Imran Saab. Well done, Dr. Saab. The forum provides a networking platform and a very conducive environment for Pakistani researchers and fellow scientists to collaborate to reach research excellence. So as part of this platform, we initiated a webinar series. Today is the third iteration of that webinar. The July and August webinars were focused mainly on business and economic issues faced by New Zealand and Pakistan. Today's webinar discussion is more focused on recent trends in technological innovations. We will discuss technologies like 5G, 3D printing, smart sensors, and our discussion will be around those things. So with that, I will introduce my panel. I have a very distinguished panel of tech gurus and researchers here today. It is my pleasure to welcome Dr. Faraz Hasan from Massey University, Dr. Aamir Mukhtar from Titanium Industry Development, and Dr. Khalid Arif from Massey University. So laying down some ground rules, the format for today's webinar is that I have allocated a 10-minute slot to each of the presenters, each of the speakers, and the speakers will talk about their research trajectories and leading to the recent trends in their respective technological areas. We will have a question and answer session once all the three researchers have completed their talk. And meanwhile, you can note down the questions, you can put them in the chat box provided on Zoom, and we will try our best to cover all the questions as we go. Right, so without any further ado, let's start with our first speaker. First up, we have Dr. Faraz Hasan. Dr. Faraz is a senior lecturer at Massey University in the Department of Mechanical and Electrical Engineering, where he leads the telecom and network engineering group. The floor is yours, Dr.
Assalamu alaikum, tēnā koutou katoa, kia ora koutou. Very good afternoon, everybody. Thank you very much, Dr. Fahim Abbasi, for the kind introduction. I'm Faraz Hasan, as you heard, and over the next 10 minutes, I'll take you through the exciting world of telecommunications. The format requires me to start with my background. So here we are. I did my bachelor's degree from NAD, Pakistan in 2008. The same year, I left for the UK to start my PhD on Vice Chancellor's Research Scholarship, which I completed in 2011. I spent some time doing postdoctoral research at KAIST in South Korea, and then a couple of years plus at another South Korean university, Sungkyunkwan, as an assistant professor. And in 2014, I came to Massey where I am a senior lecturer at present with interests in wireless communication in general. One of the first commercial deployments of wireless communication came out in the 1920s when radio broadcasting was launched, and we are using radios even today. The idea was that a big base station will throw wireless signals out that your receivers will pick up, and those signals will obviously contain the data that you want to throw from one place to another. This data travels on frequency channels. Now think of frequency channels as a road segment. If you want to go from A to B, you need to get yourself onto a road, onto a highway. Similarly, if you want to move data from one place to another, you need to place that data onto the frequency channel, which is why all of our radio channels, all of our TV channels have a frequency channel associated with them. For example, Radio New Zealand operates at 101.3. Similarly, Radio Control, which is on campus here at Massey, operates at 99.4. The same idea was adopted in the 1980s to roll out mobile phone communication. If my mobile phone wants to send something to your mobile phone, it uses a frequency channel to send that to the base station, and then the base station passes that information back to your mobile phone. This is how traditional mobile phone communication has been set up for the last 40 years or so. What I'm trying to convey to you is all wireless services, all services that use wireless communication, they require frequency channels, and a number of these services will come in your mind. All of them require frequency channels. Now, because there have been a lot of wireless services available over the last several years, what has happened is that we have run out of frequency channels. This diagram shows all frequency channels that are available and the fact that they have been allocated to a particular wireless service. I'll be frank with you, I've never been able to read this diagram, but this gives me confidence that all frequency channels that we have are in use in one way or another, which means that if I want to roll out a new service, if I want to roll out new users, if I want to connect more users onto the network, I can do that simply because the channels are already occupied. This is where 5G comes in. 5G says if the existing channels are already in use, let's go up on the frequency spectrum and use the frequency channels that are largely empty. These frequency channels are in the 28 gigahertz band and the 38 gigahertz band. And 5G says that if we start using these high frequency channels, we will get unprecedented networking speed and unprecedented networking capacity. But there's a catch, and the catch is this. At present, if we don't use 5G, our wireless signals can travel up to 1 kilometer in free space, depending on the terrain. Let's say it can travel for up to 1 kilometer. But if we start using high frequency signals, which 5G is proposing, then that range cuts down to only 300 meters, which would mean that a number of mobile phones that were previously covered by the base station will not be covered anymore if 5G is rolled out. So if I can move that onto the next slide, as you can see, the bottom two mobile phones are outside the coverage of a 5G base station. One of the questions that we are looking at here at Massey is how we can connect these isolated devices without having a base station in the middle. The idea is to allow them to communicate directly, and this idea itself opens up new research challenges. At Massey, we are looking at how will these devices discover each other. We are working on algorithms which will allow one device to discover another without involving the base station. This has never been done in the last 40 years of mobile phone communication. The base station is always in the middle, liaising all activities. Now, it will work if these two mobile phones are communicating with each other, but look at this. What if mobile phone A wants to talk to mobile phone B? Now, these two devices are so far away, they cannot communicate on the direct link. So at Massey, we are developing relaying techniques. The idea is that one of the mobile phones will act as a relay, take signals from A and pass those signals on to B through the base station. So relaying is the other area that we are interested in here at Massey. But the question is, why would this relay, why would this mobile phone help someone else? Because when I say that this relay is taking signals from A, passing them on to B, it is actually consuming its energy. So the third area of interest within 5G research is how to compensate the energy consumed by the relay in connecting A with B. And we are looking at energy harvesting. How can the relay use the incoming signals to harvest energy and use that energy to forward that signal on to B? So this is, in a glance, 5G research that's taking place at Massey, and there are a few other things that are not pointed on this slide. So simple enough, isn't it? But it's not so simple from a researcher's perspective. This is what researchers look at when they think about 5G. And this equation, by the way, is not complete. Now it is complete. Most of our research into 5G revolves around analysis. And I'm secretly hoping that nobody asks me what this equation is about, otherwise I'll be in big trouble. And this has been taken from this publication, which is done by one of the Pakistani students who finished her PhD last year. While our research into 5G is largely analytical, there are experimental components of telecommunications research within Massey as well. For example, one of our ongoing projects is designing a receiver which can pick up mobile phone signals with a view to localize victims trapped under rubble or trapped under bush. So on the diagram on the left-hand side, all colors that are not green represent wireless signals that are being received by the antenna that we are designing. And the idea is that this antenna will pick up these mobile phone signals trapped under rubble, trapped under bush, in order to localize somebody who might be trapped in there. This is the application of telecommunications in outdoor localization. We are also doing indoor localization, which means practically I'll be looking at these three signals shown at the bottom, and I'm trying to be able to tell you what is going on inside a room. This idea is known as passive localization, indoor passive localization, and it is meant to determine the activities that a particular individual might be performing without being intrusive, without asking that individual to hold on a device or an electronic tag. These two research areas within localizations are largely experimental in nature because they rely on data being collected, and then an analytical part of research proceeds after data collection. I will stop over here, but I will very quickly say that there are other areas that interest me as well. For example, we are looking at autonomous vehicle from a social sciences lens. I'm working with Imran Saab on a PhD project, which is bringing wireless communication technology with social sciences that is giving me very interesting insights into how research is performed outside my area of expertise. So with this, I see that my time is up. I thank you very much, and I look forward to your questions after the other two speakers have finished. Thank you.
Thank you, Dr. Faraz. Brilliant work. Next up, we have Dr. Aamir Mukhtar. Dr. Mukhtar received his PhD from the University of Waikato and is currently working as a research scientist in the titanium industry development. So over to you, Dr. Mukhtar. Dr. Aamir Mukhtar.
Assalamu alaikum. Can you hear me?
Yep.
Yep. Assalamu alaikum to everyone. I'm Aamir Mukhtar, and I'm from Lahore. So thank you to Dr. Imran and Dr. Fahim for giving me the opportunity to present my research. It's really a great effort. I did my MPhil in solid-state physics from University of Punjab in Lahore. And the research project was to examine the electrical and optical properties of thin films. And the material used was cadmium and from group 6, selenium and tellurium with different compositions. And the conclusion was that one of the composition was a better application for solar cell. Back in 2006, I started my PhD in material science and process engineering with Professor TiDA. Sorry?
Anna, please go ahead. Can the audience please mute?
Okay. And the research project was to examine the mechanical properties of copper-based nanostructure materials. And there was for electron microscopy, a strong collaboration with the University of New South Wales in Sydney. So the first step was to produce nanostructure materials. And when we look at the first step, it's the high energy mechanical milling was used for almost 2 years, and the powders produced was examined. So the second was the microstructure, morphology, and micro hardness, so which gives an idea that where we are going. The third step was to examine the thermal stability. So if you look at the first graph, which was produced after 2 years, the thermal stability was examined at 150, 300, and 450. And looking at the TM images, because that was also the point to look at the grain size. So the copper matrix grain size decreased with the increase of alumina. So that was the motive for the first 2 years. But the fourth step, which is quite difficult, or it was challenging at that stage, that we wanted to produce a compact. So that compact which you're looking at, it's a 25 mils compact, which was later on forged with the hot temperature, like nearly less than 1,000 degrees. Do remember that the copper is a melting point with a 1100 and alumina is 2000. So we were looking at the temperature very carefully. And then the tensile properties were examined. So the result was that one of the composition, which was later on examined by my colleague, Dr. Dingshan, and like it was giving a good electrical conductor and a better tensile strength. Okay, now back in 2010, I joined this place, Research Facility Center, where I'm working. And now the idea is why I'm showing these 4 pictures of machines. One of the reason is that it's part of my life, and this is the research what we do, those who understand. Because without these, we are nothing. So we are not based on paperwork or publications. The reason is because the students which we are getting from, if you start from AUT, Auckland, Waikato, Massey, Victoria, and Canterbury. So these all students, they don't want us to present their paper results. So it's important and legal, I think. We don't present it. Then the second, the companies which we are working for, 25 to 30 companies, they don't want their results to show anywhere. So the first machine is a scanning electron microscope, Zeiss German tool, which will give us an idea that what sort of powders we are looking at, metal powders, which is very important for the final product. Because when you look at the final product and it's brittle, the root cause may be the powder, which you got from batch from the supplier. So the chemical composition, which is the process known as energy dispersive spectroscopy, or with the solid parts, EBSD analysis, and X-ray mapping, which gives us like bulk, looking at the bulk powder, what sort of impurity you have or what sort of element you can get. So these machines are working with us for these projects. Second is vacuum sintering furnace, which is again very important for the processing. And this is one of the highest temperature furnace in Australasia, which can perform vacuum sintering. And we have also examined injection molded samples. We have done differential partial sintering. The next one is the tensile tester, which is doing tensile testing. So some few thousands of samples were investigated with the results of UTS, ductility, and heat strength. And then we have compressive analysis, flexure analysis, 3-point bending test. So I'm not doing a publicity for my place, but these are the projects which are before COVID and after COVID will be part of life. The last one is the 3D printer machine, which is like a different process, selective laser melting process. And I'll talk in the next slide. One thing which I want to show, that there was a project, I was just talking to Dr. Imran from Massey University. So there was a jawbone which was built in our office for a dog. And that was implanted in that dog. And there were a few others afterwards. So that was 5 years ago, this project. So it's very important. It started from powder, it's TI64, and then it ends in a final product. And at the bottom, we have about this here, a 3D robot, which is with wire arc additive manufacturing. And if we were looking with the 3D printer at the small parts, now we want to look at the large parts, and not in argon. And my job is to examine the tensile and fatigue properties. Okay, so the project, we were lucky that we were able to publish at least one major project of nitriding of titanium alloy. So the question, we asked questions before putting in all these projects, that what is the purpose of nitriding titanium alloy? Before that, the different companies, they were using laser nitriding, which is very expensive. So we used nitrogen gas. I worked with the German scientist, Dr. Peter Franz, for 3 years to bring this, you can say 4 different variables to control temperature, to control time, to control the pressure, and then the flow of the nitrogen gas. So that was published 6 years ago. And if you look at this dark gray color was changed to golden brown, the heat treatment done, and it was part of the Team New Zealand kit at that time. And you can also see that image Tom Cruise wearing in the kit. And then one other thing which we examined in the last 3 years, that nitriding is not applicable to all applications, especially not for the rotating objects. So looking at the fatigue analysis, we got an idea that the fatigue strength is low for the nitriding parts. And we have shown some fracture surfaces and fatigue cracks. Coming back to the 3D printing, which is the most important topic for the last few years in New Zealand and over the world for 2 decades. Look, the additive manufacturing process, there are 4 or 5 which are very commonly used. We use selective laser melting process, SLM. The machine SLM which we have is EOS German machine, and that's not for commercial, it's for research purpose. You all can bring your own projects and we can work for it. And different powders, especially we are using titanium. So if we look at the, you can write on 3D printing on YouTube, you can find many videos. But just to tell you that this window which you're looking at, when this recoater moves left and right, it brings powder into the machine. So then this goes to the basic point. What size of the powder, which is very important. 80 microns is the particle size. So if this solid, which is built on a solid part, which is built on a plate, it may be 36,000 layers. And this part, which you're looking at on a plate, different one, and one single is this part, like what we used to examine. Now, when it is built, the first thing is to check its strength. So there must be some bars on each plate, which we check the tensile testing. And then the other step is to look at the cross-section of these parts. And looking at the cross-section, like this picture which I'm showing you, it shows that the layer is 135 micron each, almost average. And then again, it goes to the electron microscope analysis. So that's the different projects which we are doing. And just to show you that 5 years ago, we prepared one of the titanium pen with some names on it. So I wrote Imran Khan and presented a couple of years ago. There was a titanium medal on which Pakistan was written. And yes, it was given to students in Hamilton. Then, the other part which I want to show, that's a titanium
the end of time, almost.
Sorry?
We're almost out of time.
Yeah, just last slide. Okay, so that's a titanium globe. And just to tell you, because each plate has a different cost when you're making it. And that's a very important thing to look at it. So roughly this is $800 if you make only one on a plate. But if you make 2 or 3, the cost will definitely reduce. Okay, the last slide. And yes, we all know after COVID that we don't live in an ideal world. There's no ideal world. So now the world will be different. According to the Spanish architect Vicente Goulart, who designed a city 180 kilometers south of Beijing, and it's for the next few like decades. Maybe few countries will follow it. The best thing which I like for this project is that they're defining that the ground floor will be defined for 3D printers as a workshop. And the people who will be working in it, they live upstairs and they must have a room in their house where they can work with it. So yeah, that's it. Thank you very much for your time. And over to Dr. Fahim. Thank you very much.
Thank you, Dr. Aamir. It's really exciting stuff. So our third and final presenter for today is Dr. Khalid Arif. Dr. Khalid is a senior lecturer at Massey University. He's working on smart sensors, robotics, and additive manufacturing. So without any further ado, the floor is yours, Dr. Saab. Dr. Khalid, you're on mute.
Okay, thank you, Dr. Fahim, for the quick introduction. It's a pleasure to be presenting about my work to this forum. And again, also thanks to Dr. Imran for arranging all this one. So I'm going to talk about sensors and smart systems. This is one of the areas of my research, taking most of the focus pre and post-COVID, probably no post-COVID, during the COVID, the situation. Here's my quick background. I've been around quite a few places, starting from University of Engineering and Technology in Lahore. I've been there in many different, roles, from student to lecturer and assistant professor at some point. And my education really from UET has been going to Tokyo for my master's in 2002 and to 2004. And coming back to UET and then to Purdue University for my PhD. Then there was about a year back to UET. And since 2012, I've been at Massey University. So currently I'm senior lecturer in the same department where Faraz, he already mentioned, mechanical and electrical engineering. Okay, so I'm going to talk about sensing, and I would start with this very well-known quote from Lord Kelvin that if you cannot measure it, you cannot improve it. And this has been valid for a long time, whether we're talking about, telecom, new technologies, 5G, or materials for printing and other things. They all really come to, you have to measure before you can do any improvement. And especially, in the current times where automation, where AI and all those are taking most of the attention from researchers and industries moving towards those, it's important that we can reliably measure, and I think that's what really makes it a basis for doing research for me in sensing area. Okay. Look, what is around us, there are so many sensors. So in our smartphones, in our security systems for home monitoring and whatnot. These sensors are there, and many of the sensors are developed to a level where there may not be more room for pushing the physical measurement limit. Okay. But as the technology is changing and moving on, new materials and new electronics and new ways of miniaturizing or making arrays of these sensors are coming, more research is needed, and that kind of pushes this direction forward. Okay. So because sensing is actually well known, so without giving a lot more detail here, I'll move on to what are those topics that really are going on in my lab, or I've been working around the sensing topics in last couple of years. Okay. So water quality is one of the prime research themes in my group, where we use optical and electrochemical and whatever other methods is suitable for deployment. You can have in rivers or water monitoring in the drinking water or the process facilities for treating wastewater. Then air quality is also one of the topics I'll show later on, where this has gone. In this case, we're really interested in bringing this, the air quality or indoor air quality especially, to a level where you don't have to really rely on the digital units or just go with installing one unit here and one there, while the surfaces And maybe the materials of future can have sensing capability in them. That's the kind of the aim. Then, because all these sensors would eventually require electronics and integrated, processing and on board. So that's why CMOS is also part of the topic. So designing on wafer and, integrating at high level. And there are examples as far going into more like making the system based on the IoT, so that you can acquire the data and you can analyze and you see what's going on. So a lot of topics in sensors are listed here. There are many more. This was the first one was did at Massey University in collaboration with Callahan Innovation and a company named Miller Limited based in University of Auckland. So this one is related to biomedical rather than air and water. In this case, this sensor is focused at or aimed at very specific condition in some of humans called hydrocephalic condition in the brain. What happens in this condition? The white fluid in the brain starts kind of, let's say, increasing in the volume, and the pressure built up inside the brain. And because of that, people have many different situations. They could be coming from an injury, could be around like an accident or some sort of explosion, or it could be congenital coming from birth. Now, what surgeons do, they would measure this one through MRI or CT scans and then put a shunt, really like a little tube inside the brain from the back of the neck, and then take out the excess fluid. So this is done repeatedly, and many times those patients with the advanced level of this condition, they may have this little tube hanging behind their the neck, and maybe like a big kind of lunchbox style device or even bigger one. So they have to carry. So the mobility is really kind of limited if you have this kind of the instrumentation around your body. So in this case, the idea is, can we have an implantable sensor that can go under the skin? So the bone on the skull. So really it's like drilling a hole and putting the sensor in there. It stays in there and works for a long time, ideally for like up to 10 years. But then you can do the wireless measurement from the sensor, so the person can move around whenever the pressure is more than the needed, the required in the body. So the patient can go back to the hospital, and then the surgeons can still do the shunting process. So this was a project done on from the basic, let's say the design and analysis to fabrication. And because it was with the company, so the company is taking over to the next stage now. And my student who finished in 2019 moved on to McDermott to his postdoc. So this has been one. The reason moving on from this kind of research, which also links to my background from Purdue University, to water and air, is because water and air is relatively easy to do in an engineering department, while anything related to biomedical really requires very strong collaboration or facilities that are suitable for bioresearch, which was not the case, especially in the Auckland campus where I work. So moving into water and air was a consequence, or more like a choice that was forced on me, because of the lack of the facilities. Okay. So in water, because water is so important, and most of the research in the country now, from science challenges to MBI, smart ideas and all, is focused on water and other sensing in agriculture. So this has become very valuable topic over the years. This diagram shows here what we really do. I mean, I don't want to get into that detail, but the point is, we use techniques around biosensing, electrochemical, and optical, whichever works really. Based, I mean, this depends on the application. In this case, what we're looking at is, we get a contaminated water sample, we put that through our fluidic system, which we make ourselves. And over time, if we can capture the analyte, for example, arsenic or E. coli and whatnot, on a surface, we can explore that with optical methods. For example, in this case, it's laser diffraction. So we can measure the intensity of the diffracted modes and then link it back to how much the quantity of the analyte was in water. Okay, so I'll take it to the next one. So this is one example. I mean, how the process goes on. There's the biochemistry there, the surface chemistry, biochemistry, how these chemicals will bond with each other, and what analysis steps are done from fluorescence microscopy to normal microscopy. Now, since that's one way of doing it, because I've got some background in 3D printing, at some point, like 3 years ago, realized, can I really combine both 3D printing with the sensor making process, so we can have this whole process like a low cost and very efficient and speedy. So in this sense, we've started working on printed sensors through a technique called electrohydrodynamic printing, which is a form of 3D printing, but this can give you a resolution, very high resolution, which I'm going to show here if this video plays. So we're really looking at about 180 to 100 micron wide lines printed out of silver ink. So we can actually print these electrodes, instead of going into a microfab process, we can print these ones and with the desired properties, so for air or water or whatever. Once that's done, you can interface with the electronics and you got a sensor working. So it's a kind of a different way of doing sensing by combining printing, new materials, and having an objective of, a particular sensing. So they are,
sorry to interrupt. We run out of time.
Yeah, so this is kind of last one. Okay, so these are some of the examples of the features we've achieved. In a normal, room temperature environment, we can get to a 2 micrometer, which would normally, require you to work in a microfab facility. Okay. So I was talking about earlier IoT. This is one of the examples of, working with air quality with different partners around New Zealand, making sensors for them so they can have houses or schools and that monitoring for different parameters in air quality. A list of a lot of collaborators worked with, and since running out of time, so I'll come to thank you. Any questions? Oh.
Thank you, Dr. Khalid. That's great work. So next we move on to the questions.
Yeah, okay. This is Moin Khan. Can I ask a few questions, please?
Go ahead, Mike.
Okay, very interesting. Sorry I was late in joining. I wasn't that smart in sensors, I think.
We have it recorded for you.
Great. I think it's a great work you have done, bringing all knowledge together. All our compliments to you all. Keep the good work going. I was just listening to Dr. Khalid. Dr. Khalid, can you also work on earthquake sensors? New Zealand being a very susceptible area for prone to earthquakes. Do you have some plans to use sensors in monitoring earthquakes?
So do you see my screen?
Yeah.
Yes.
So this is a seismic sensor that I'm working on, and then like we're making these ones. I work with process industry monitoring, wine fermentation and other, the more like from the process point of view. But this is one of the topics for seismic monitoring. Okay, so this is more like it is not really intended at the moment, for earthquake monitoring, but this is for intrusion and the fall of people in old age facilities. If person falls, currently what is done is you put a band or something, or maybe put like a camera in the environment, which is not very useful in many cases, because if the person is not wearing that device, you wouldn't know if there's a fall or not. But if I can install this one, this is more like a peg to install in a surface, in a garden or wherever. So you would know, you can really kind of filter out, the big vibration produced because of the fall. And this is also towards the, the earthquake measurement. Yep, it is there.
And another area, is blockchain an area of interest for you?
It's blockchain is, and there's been like I know a kind of a little bit around this one, because we have one PhD student working in this area. For the time being, haven't done anything around that, because blockchain, and especially what they call the more like computing and all those, probably I need to go with Faraz at some point, so we can get into those areas. But I know that could be quite useful, bringing into, let's say, my sensing research. Or
I'm involved in halal certification.
Mhm.
This is where I feel blockchain can really contribute in traceability of halal products. So if you can work on this, it could be a good halal cause.
So, excuse me for this one, but from what angle you are really talking about blockchain and halal food? Are you talking about it's like a sensing something and being able to, what do you say, have the authenticity?
Yeah, traceability.
It's
That
traceability. It's
that
there are multiple applications of blockchain around traceability, all the way from the farm till the table. You can trace everything at every step.
Yeah.
So sorry, I have a lot of other questions as well.
Yeah.
So
Okay.
Dr. Zulfikar Buttsab has raised his hand for a question. Dr. Sab, please go ahead.
Yes, thank you, Dr. Sab. Let me start by praising you guys, Dr. Imran, you and the team who has arranged such a wonderful opportunity. And thanks to all the presenters. My question is from Dr. Faraz. And sorry, I missed the first slide, but my question is regarding third or fourth slide. When he says that all the channels are taken in the bands, I want to ask, is it really a limited resource for the whole world, or he was talking about the New Zealand bands only? If it is the same resource or quota for the whole world, who controls it?
Yes, alaikum salam. Fantastic question, what's up? So I was talking about the entire world. The way the frequency channels are handled is that every government of every country has responsibility of making sure that the right channels are allocated to the right services. In the interest of interoperability, if I take my mobile phone to Europe, and if two separate frequency channels are allocated for the same purpose, one in New Zealand and one in Europe, my mobile phone will not work over there. So there is a lot of cooperation between the governments to make sure that the same service that has one frequency channel in New Zealand also uses the same frequency channel elsewhere in Europe or elsewhere in the world. There are slight differences here and there, of course, but this is the main operating principle. When I say that we are out of frequency channels, I'm afraid we are out all across the world, not just in New Zealand.
All right. Thank you. Thank you. Lovely.
Right. While we're on Dr. Faraz, I've got a quick question for you. 5G has been a big thing in the media lately, especially around COVID. It's a millimeter wave. It's a really small wave. And there's a lot of conspiracy theories that, that wave could actually knock out electrons and, molecules inside DNA, and they can mutate and cause all sorts of things. And we've seen these really savage videos and pictures of people mutilating these 5G towers and burning them, especially in the US and thereabouts. So what's your take on that? Is that really true?
I have spoken to a number of media outlets on that, and my take is that we do not have enough scientific backing to say that 5G causes damage, particularly COVID-19. I was talking to Fortune, and they specifically asked whether 5G causes COVID-19 or not, but it doesn't. There are a few papers around that somehow prove that there is something messy going on in there. But the devil is really in the detail. If you dig further into how they are doing their research, what is the methodology, what are the assumptions that they're taking, most of the papers that I have seen, I don't claim to have seen and read everything, but the ones that I have seen, they have major flaws in the methodology or in the assumptions that they are taking and so on. This is the take of the governments around the world as well as non-governmental organizations, World Health Organization, Ministry of Health here, and others also have reached the conclusion that it is safe.
Thanks for clearing that. Do we have any other questions?
Can I just pitch in?
Sure.
I look after a business school in Karachi. I was just wondering if I give a topic on 5G and supply chain. Can I take some help from Dr. Saab?
Sure, I'll be very happy to help, certainly. And on the traceability of halal products, that's again something that interests me, because one of my areas of interest is intelligent transportation systems. my PhD actually is on ITS and vehicles communicating with each other, fleet management and all that. So if we can catch up after this, that would help a lot more inside.
Okay, that's great. God bless you.
Yeah, just to reiterate, the purpose of this platform, this forum, and this webinar series is exactly this. So we want to create these linkages. We want people talking to each other. We want people sharing, exchanging ideas so that
Great.
we build these linkages and, you know, move forward collectively.
Jazakallah.
Any other questions?
Imran sir has 2 questions.
Yes, Dr. Saab, go ahead.
No, we can't.
hear
There
you.
is a sound, but that's not yours.
Dr. Saab, I can't hear you. What I'll do is that I'll read out your questions, right? Yes, now it's all good. Go ahead, Dr. Arif. I think.
So I know Dr. Aamir can answer this question on 3D printing, but okay, Dr. Aamir, please let me add a few words and then you can explain further because you probably have more like overlapping background here. Imran Saab, the answer is no, there is no 3D printing that can print houses. That's the answer. But you can print parts of houses. You can print with the technology if you want to print full houses or complete houses. Those are more like for emergencies. Those are for refugees. Those could be for military and those kind of applications. If you're talking about normal houses, the problem is not only the structure, but the materials. So you have lots of materials. You're not using mortar and bricks only that you can just keep on depositing the material. So if you're talking about proper insulation, breathing, the indoor, quality of, you would say, the environment, okay, and all those, then probably we are too far away from that point. I think that was my answer, but now Aamir Saab can add a lot more to this one.
Yes, it's very interesting question, Dr. Imran. Look, 3D printing, first of all, we just have to get an idea. 3D printing is anything which moves in 3 dimensions, number one. And the 3D printing machine, which is roughly $1.2 million, is basically for small parts, which has a restricted area, like 40 by 40, 400 by 400 mils, and up to 220 mils height. So that's the main thing which 3D printing is defined for. However, having said that, the second tool which we have also got, the wire arc additive manufacturing, which is using a small arc, maybe, but now it should be easy in next few decades to build large structures. But housing, it may be very difficult because that you have to bring a large infrastructure, like you have to get 50 to 60 robots for making 4 or 5 houses. But who will pay the cost? And then the second thing, you'll be losing your labor force from the market.
Yeah.
You have to reduce them, finish them, or maybe, and then bring this technology back into it. So for housing, it's very difficult, or maybe slightly impossible after this COVID. If there will be no COVID, then there was many things possible in this world, in this ideal world. So
just to
yeah,
follow
that's my idea.
Yeah, just a follow-up question on that. I've read somewhere about Mars explorers or all these space exploration, the astronauts getting equipped with 3D printers so they can literally print their own houses, gonna live in, or print out parts for the rocket. So how far-fetched from the reality is that?
No, that's totally true. You can do that,
Yeah.
but now you're talking about a specialized application. So
Yeah.
you're talking about like printing with certain materials and printing for certain purpose. Like the house at Mars, have totally
That's
different
right.
requirements. And so we did one project in the last 4 years with Fiat Food Industries Enabling Technologies, printing insulation around milk vats. And you can imagine the size of milk vats is like a 3-4 meters tall, and the diameter is again like 2 to 3 meters. So printing the insulation all around that one. And the biggest challenge is not designing a machine. The biggest challenge is the cost of the material. So whatever Dr. Aamir Sahib is telling, that the smaller parts, if you scale that up, you would be spending millions of dollars for something that rotational molding can produce for like $1,000 or $2,000.
So it's not feasible anymore.
So materials, okay.
Yeah.
I just want to add one thing because we were looking at some projects. Like for example, if you're looking at the satellites which are revolving, the fuel tanks are now being built by 3D printing. So that kind of project can be specified because that's a specific research.
Yeah.
Second, last week, Dr. Khalid might be definitely have an idea. Their university engineers, they have produced a 3D mat. A 3D mat, so that means that in next decade, the aeroplanes or aircrafts, they don't need a runway. You can define 3D mat on a desert, in simply grass, any area. And these kind of projects possible because they bring cost and all these things into the market. But for housing, it will be difficult.
Yeah, but
That's a good idea. There is a possible after a scenario after 10 years when this COVID and all these things will finish, you'd start making like Khalid Sahib, like just like wire arc, you place a different material inside it, and robots can build it house. But then,
but the crazy thing is that I saw on Amazon or maybe Alibaba some site that you can buy a 3D printer for $600. I mean, it's
you can buy even cheaper, but those are for tiny, small parts, and you will really be like, look, you can buy for $600, but you would become a mechanic over time, because it's a really simple thing, buy the cheaper ones, they will work for you, but you'll be learning 3D printing and printing some basic models and prototypes.
Right.
So
I would just like to add, one of the reasons Pakistan steel mill failed was lack of spare parts. They were dependent on Russia and they wouldn't get it at time. So they are now reviving Pakistan steel. So this could be one of the area of interest, having 3D printing in their design bureau so that when there are critical spare part fails, they can use this 3D printing to develop. So that could be.
Minds up that just adding to that one, not only printing, but there's one thing called additive subtractive. So you can repair the parts that are broken a bit. You can add material to those ones. I think Germany is actually investing, I think maybe the biggest chunk of their research effort into this area, because you have a part, one tooth is broken from a gear. Can you add that one? And so there are techniques around that one for, laser, the melting and laser deposition of the metallic powders on that one. So yeah, these are the areas.
Yeah, I think with all your expertise, there are so many areas waiting. I think great.
Yeah, definitely a lot of synergies here. It's a great environment. Any other questions?
May I jump in on the congestion side of things that Imran Sahib raised?
Yeah.
So 5G can certainly contribute towards reducing congestion. How? By continuously monitoring the traffic situation, feeding all that data into algorithms that can predict what might happen 1 hour from now or 2 hours from now. But all that requires a lot of data going up and down the network, which present networks can't sustain. They are already overburdened with the usual data communication. They can't tolerate this additional amount of data going up and down. But with 5G, because we will have increased capacity, there is a possibility that we will be able to handle that data and predict what might happen moving forward. But again, 5G can go as far as saying, yes, congestion will be there 1 hour from now. Please choose an alternative route. But having an alternative route is not a 5G problem. That's a transport planning problem, isn't that right, Imran? So I think the prediction side of it can be handled, but planning an alternative route, that falls under another area of expertise.
Yeah, I can answer the same question from a different angle. It'll be very quick. So let me share my screen. So Imran, this is the solution. This is one of my ongoing projects started a couple of years ago, 2.5 years ago. So electric vehicle, golf cart, autonomous shuttle. So this is, okay. So this is kind of the work we do, not only how the vehicle goes around on the roads, what happens inside, inside condition monitoring is here. And yeah, so, and then the team has already won a big prize in engineering New Zealand. Okay. So this was the GT Murray's award presentation. They were transport. So this guy here is actually the Auckland Transports, whatever the position is, CEO or whatever. So this is really one way to reduce congestion, because when the 5G comes in, that's all, I mean, this will depend on, the being able to communicate with the other vehicles and, negotiate the path, So current problem with the human driving is, you can tell that this side is congested, don't go there. But the mind itself, you don't do that one. And that's why the congestion keeps on increasing. While if the vehicle can talk and drive themselves, then probably you can manage. And also the speed is really good. If the vehicle can go fast, because slow is a problem again, and what distance between the vehicles. So there are many challenges around how you can solve this one, but this is one way we are trying to do this from my group.
That's excellent work. Especially Tesla is doing a lot of work in this area, and every day is a day in Tesla. Every day they're pushing out new models, getting automation done, and I think that you have a Tesla golf cart per se.
Yeah, so this one, I mean, we now designed it for 3D printing. Aamir, this is for you more interesting again. So printing the whole thing, with 3D printing, okay? Because in our previous research, we were able to produce some low-cost materials from rotational molding, polyethylene and HDPE, high-density polyethylene, low-density polyethylene. So combined with that, because those are really low cost, that's why you can have bigger tanks for water and other things for like a very normal cost. So we're bringing that side down so we can add that material and probably construct, bodies around things.
Excellent, excellent.
Are you doing something about lithium in the battery? Because in electric cars, battery is a big area of risk where you can't have lithium available in future for the batteries.
Yeah, so I wish I could work on that too, but there are other colleagues working on those things for energy storage and capacity enhancement. But we really use the battery. So my golf cart has 48 volts, 8 batteries, 6 volts each. That's what I know.
That's great work. You know what? Taking one step back and looking at the bigger picture, what I see is that we've talked about wireless communication technologies. We've talked about 3D printing. We've talked about applications of 3D printing in terms of housing and for different parts and stuff like that.
Yeah.
We've talked about autonomous cars. And you know what? If I put them all together, all these things in one string or in one box, then the bigger label that I can give that box is a smart city.
Yeah.
So my suggestion to Dr. Imran Saab is that maybe in the next couple of months, we could have another session around smart cities, which is the actual implementation of technology towards urban living and trying to optimize a whole bunch of different areas within that. And I think we just have our last minute, Dr. Imran, if you want to say something. Thank you, Dr. Shah, for organizing this. So once again, I would like to thank all of our presenters for today, Dr. Faraz, Dr. Khalid, Dr. Aamir, Dr. Imran, for your support in organizing all of this. I know it's a lot of hard work in the back end. We don't get to see that hard work, but yes, it's a lot of hard work setting up the presentations, connecting with the people, organizing everything. And with this whole COVID situation, doing stuff remotely is now, kind of becoming the norm. So with that,
Can we share the email addresses so that we can keep in touch?
Yes.
Yeah, that's a good idea. Dr. Shah, we can put them on our Facebook page.
Thank you to Mr. Moin for joining from Christchurch. Thank you, shukriya.
And then, sorry, I was late, but I did manage to
And to my colleague Cognelia from California. Thank you very much.
Oh, we have a very global kind of audience. That's perfect. So guys, this is exactly what this is for. So this is your forum. So go ahead, ideas, talk to Dr. Imran, let's get the ball rolling. He started something. Let's, add our value to it and get things, make things bigger together. So with that, I would like to thank all our presenters, all our audience, and then again, the New Zealand Pakistan Research Forum. And thank you all, and see you again next month.
Great.